we don't have Calc 3 here. And I don't know of a school that offers it besides going to CCAC to take it there. But here is, so these are like the multi-dimensional pictures. Focus a little more. And the one on the left, maybe, there it goes. So it shows you what a solution will look like with 1 point. So we typically have, like, pretend the red is the, like, our y-axis, the x will be the orange, and then you have, like, the blue being the z-axis, and how they're connecting at 1 point. So they still are meeting in a middle, in a center point. And that center point is when you have a solution, one solution. So the other options, we'll kind of see why they would happen. But down on the bottom, it says the solution would be one whole line. And that happens when we could have infinite solutions, because every point on that line would work. All right, so if you look at the question that we're going to be working on, or the type of problems that we're going to be working on, as it says, this above system is called row echelon form. So it's a form that we're going to try and get our equations in, because it's kind of a systematic way for us to solve. And row echelon form happens when you pretty much have 3 variables, and you go down to 2, and then you go down to 1. Or if I had 4, my next equation would have 3, the third would have 2, and the last would have 1. But you're losing that lead variable every time. In order to do that, we use something called Gaussian elimination. Carl Friedrich Gauss, he was a mathematician in the 1800s. He created a couple of different concepts in math and geometry, but the elimination is one that he's kind of known for. And we're going to do this, there's many ways, and Virginia said she, you remember doing it in what, maybe Algebra 1? But using substitution, where you're trying like get one letter equal to something and then take that expression and plug it into the other one, but there wasn't really a systematic way to always go about it. So the book suggests leaving the x in the first equation, pretty much keeping the first equation the same, but then eliminating the x's underneath it. And if you do that every single time, and the same process every single time, it does actually save you work, and it makes it a little easier, especially once we get to the 4 and 5 variables. So if you look at our first, we're going to just look at the first 2. You can only use elimination with 2 equations at a time. You can't try and eliminate a variable from all 3 at the same time. So looking at the first 2 equations, what could you do with those first 2 equations to get the x to eliminate, Brandon? Just add them together. So we're going to take those 2 equations, literally we're going to add them together. Because we have a positive x and a negative x. And it's okay that there's not a z, because our goal is to eliminate x. So we're eliminating the lead variable. So each time we're losing that lead variable. Brandon, when you combine them together, what do you get?
3y plus, wait, no, y plus 3z equals 5.
Yeah, y plus 3z equals 5. That new equation, while it still has 2 variables in it, the x is eliminated. So I'm going to try and show you like this stair-step approach. So here's the original with a z, not a y. And then the new equation that Brandon gave me is called your resulting equation. Because it didn't solve for one variable by itself, but at least it eliminated that x from the first part. So now I have at least what looks like a stair-step. We have 3, and now we have 2. So this resulting equation has replaced the second equation. We now have a new second equation. So we're going to go back to the original 3, and our goal is to eliminate the x now from the bottom. I always use the first equation every single time, but you don't have to. So you could use the second equation and multiply it by something in order to eliminate the x in the third. But I just always go back to the beginning and I work with the beginning. Again, I'm systematic. That's what a math person, I'm a math person, totally math. Everything has to be a system for me. So Brandon, what could you do if we were to eliminate the 2 from the third equation? X, so we're only working with x. So we're going to eliminate x from both of the equations. Yeah, so we're going to multiply the top one by 2. Yeah, -2 would work better, sure. So the top equation is now negative 2x plus 4y minus 6z equals negative 18. The bottom equation, Aaron, do you need a pass?
Probably not.
Okay,
You okay?
great, thank you. So again, the goal is to get rid of both x's. So the x's are gone, we're left with a negative y, a negative z, and a negative 1. So here would be my new set of equations, where we've taken the first one, it stayed the same, but we eliminated the x from the 2 underneath it. So these two equations, the ones underneath, that x was eliminated, which is the goal of this Gaussian elimination, trying to eliminate one whole piece from the problem. Brandon?
Does it matter what equation you replace it with? Like whenever you the first one and you got y plus 3z equals 5, you replaced it with the second one, do you have to replace it with the second one, or could you have replaced it with the first one?
You could have replaced it with the first one, yeah, it does not matter.
Okay.
I'm just making mine follow the stair-step pattern.
Okay.
But no, it does not matter which you replace it with. Other questions? So we've eliminated the x variable, and we now have two equations that have the same variables in them. They both have a y and a z. So if you eliminate the same variable, you should have two equations left that contain the leftover variables. Our goal is to solve. So how would you continue to solve? Virginia? How can we get rid of the y? Yeah. So if we take the new equations that we created and we eliminate y just by adding those two equations together, then you should have z by itself. So we've got the y plus 3z is equal to 5. That's a negative y minus z equals negative 1. So adding them together, y eliminates, 2z is equal to 4. So z equals 2. And that's going to be your goal, to get one variable by itself in the end. So we eliminated the x's from the second and third equation so that what we had left had just y and z, but both of them had a y and a z. So as long as you eliminate the same variable, your two remaining equations should have the same letters remaining in them, so that you can then use those two. So really we did substitution 3 times, or I'm sorry, elimination 3 times. Now we're going to use substitution, because once you have an answer, you substitute it back into one of the previous problems to continue to solve for the leftover variables. So the y is positive over here, and y plus 3z equals 5. So y plus 3 times 2 is 5. So now y is negative 1. Going back into one of the original equations that has an x in it, x minus 2 times y plus 3 times z is supposed to equal 9. And it ends up giving us a positive 1, which is the same as the original problem in the warm-up that we started with. It's just that problem was already in the stair-step form. Questions? Lily?
Okay, so this is like kind of question, but like not really.
Okay.
But so I get how you do it, but like why does it work? Like what's like how?
Because you are eliminating the same letter. So when you eliminate the same letter, you're left with two equations with the leftover variables. So if you said, well, I want to eliminate x from this one, but y from that one, then you're going to have two equations with different variables because you eliminated different variables from the problem. And as long as you're like systematic and you try and wipe out the same variable, then what you have left should be a shorter equation that you can continue to use regular elimination. Does that make sense? So elimination means you want to get rid of a letter. And as long as we continue to get rid of a letter, then we should be breaking the problem down. And every time you break down the problem, you have something less than what you started with. Virginia? You can use them in any order. I just like to stay the same so that I know that I'm not going to make a mistake every time, and I just use the same system. That's just me. My house is obviously very organized. It's because that's how I'm made. It's my mother made me that way. She's very organized. All right, so let's try it again. If you flip and look at example 2, it gets a little easier, like once you kind of see it just a couple of times. And I think as long as you try and use the same process, it really does, it's like, see, it's just like, oh yeah, that makes sense. So, all 3 equations have an x, y, and a z. If you start in order and try and get rid of the x in the second equation, then we should create that stair-step problem. So, Eris, if I wanted to use the first equation and the second equation, how could we use the first to help us eliminate the 2x underneath?
Multiply it by -2.
Yeah, so take that first equation, multiply it by -2. So -2x plus 6y minus 2z equals -1. The second equation stays the same. Sorry, thanks. And then Eris, when you add them together, you get
5y minus 4z, 0.
good. So that is a resulting equation. We got rid of the x. So try and do the same thing with the third equation. So Michael, how did you eliminate the x from the third equation?
Well, I multiplied the -1.
Yeah, so either one. Did you multiply the top one by -1 or the bottom one?
I multiplied the bottom by -1.
Yeah. So he kept the top one the same. Multiply the bottom one by -1. And Michael, you end up getting?
-5y plus 4z equals 2.
Sure. So -5y 4z equals 2. If you multiply the top one by -1, you should end up with a positive 5y and -4z equals 2. Jeez. Brandon, what do you think?
Whenever you go to solve for y or z, the variables just cancel out and you get 0 equals 2, which is no solution.
Yeah. So now that you have these 2 equations with the same variables, you're down to that like typical type of elimination that you've done since Algebra 1. Adding them together, because the values are opposites, we have a positive and negative of each y and z term, you get 0 equals 2. And 0 can never equal 2. So therefore, there is no solution. So when there's no solution and you have 2 lines, that means the 2 lines are parallel and they never connect. When there's no solution and we have 3 variables, it means that they could connect. 2 of them might connect. So 2 of them are connecting in the same spot, but the the third one isn't meeting in the same spot. So yes, they're all connecting somewhere, but they have to all connect together at the same spot for there to be a solution. The other option it shows you is, and this is really hard to visualize because it's 3 separate dimensions. So thinking back to geometry where you have a plane and then you have a different plane. A plane is considered like that flat dimensional surface. So they're like 3 separate planes that are kind of just like floating on top of each other, which is kind of weird to visualize. But that's where like no solution would exist. Remember talking about planes in geometry? All right, so one more problem with this elimination. Are there questions on example 2? So if you look at example 3, why would number 3 be considered like a nice example to work with? Kate? Yeah. Without doing anything, the x's are going to cancel. And the second equation doesn't have an x in it. So like you need to use elimination once here to get the x's to cancel from the first and the third problem. So Kate, if we add 1 and 3 together, what do you have?
3y equals, or 3y minus 3z equals 0.
Yeah. So adding 1 and 3, she said you get 3y minus 3z equals 0. The second equation we're not doing anything with because you already have a y and a z by itself. So this works because you're taking out a variable and what you have left, they have similarities. So what would we do to solve the remaining, Brandon?
Multiply the first one by -3, and then you get 3y minus 3z equals 0, negative 3y plus 3z equals 0, which would get the solution again. Wait, no, 0 equals 0. They're
Yeah.
the same thing.
So this one we end up with 0 equals 0. And when you have 0 equals 0, that means we have infinitely many solutions. However, we have 3 variables. When there's 2 variables, you can pick any x and plug it in and get out a y that depends on the x that you choose. But when there's 3, you can't just pick a random x, y, and z. Because you have 3 different variables and they all kind of depend on the other. So you pick an x, but then you have to pick a y to get a z to work. So we actually have to write our solution as an ordered triple with a special pattern. Because it can't just be any random set of numbers. So we're going to see if we can find a special pattern related to the answer. So you can't stop at infinitely many solutions and be done when you have an ordered triple or 3 solutions. So if you go back to this equation right here, the middle equation, what does that middle equation tell you about the answer? Brandon, let everybody think. Thanks. So right now it says y minus z equals 0. Okay. yn? Yeah. If you take the z to the other side, you get y equals z. That means your y and your z have to be the same number, whatever they are. Both a 2, both a 5, both a 7, both a -3. But both of them have to be the same number. We're going to try and write this as an ordered triple, but instead of putting the y and the z as your ordered triple, because then I'm using still the variables in the equation in my solution, we are going to instead kind of insert a random value to recognize or represent the z variable. And I'm going to like define it for z because z is the last variable. That's usually the one you're trying to solve for first. So we're going to say, that's a let z equal a, and a is any number. And you're going to see that used a lot as you kind of approach higher level math. So if we're trying to just write like an ordinary, a basic, a generic equation or a generic representation of a point, usually you just say, all right, let's just use the letter a. So we want a to be consistent in our answer. So if z is equal to a, in my ordered triple, I'm going to put an a where z is usually located. Kate said y and z are the same, so that means we'll have an a as well for y. So now I have like this pattern where I know that a can be the same. So it can both be 1, it can both be 2, it can both be 3. How can I figure out what x is? Virginia?
Would you plug A into one of the equations and then find x?
Yeah, so go back to one of the equations that has an x in it. You can use the third equation, God bless you, because it just has an x and a y. Or you could go back to the first equation as well. But the third equation has less in it. So my third equation says negative x plus 2 times y. Well, y is a, and then that's equal to 1. So if I solve for x, x would be equal to 2a minus 1. So that gives me a pattern as to how we can represent each variable. Instead of saying x, y, and z, it's at least using the same like generic letter to represent. Those are going to be the more difficult ones to think about. But if you start with letter z, so start with z, get your equation in the z equals. So z equals a, z equals 5a. It's not always going to be a by itself. And then move your way backwards from there. But z is usually that first goal. Our goal is to get z by itself, and then we kind of use back substitution. Questions? So we are going to kind of just briefly talk about a matrice and how you can check your work using the matrices in the calculator. We're not going to multiply by hand, which I totally let down 7th period. They were like, what? We're not multiplying by hand? I guess they have high expectations for me. Since I never let you use the calculator, everybody's used to not using the calculator. But if you pull out your calculator, flip to the next page. Just going to kind of review with you how to set an equation up in a matrix. So a matrix equation, or a system of equations, can be placed in matrix form by using the coefficients that are in your equations. And you're going just through the first equation and listing the coefficients. So going horizontally, the coefficients of my first equation are 1, -2, and 3. And then we have a -1, a 3, and no z's, so we place a 0. And then finally a 2, a -5, and a 5. So you're just taking the coefficients. The variables that we're solving for are x, y, and z. They go vertically because multiplication has to have those inner values, the columns and the rows lining up. So that's why they get listed vertically. And then the constants are the number on the other side. So in your calculator, if you take it out, you're going to hit the second button in matrix, which is that x, -1. And you're going to go over to edit and hit enter. It's a 3 by 3. Enter those data values in. So it's second x, -1. You're going to do that a second time. Second, quit first. Second, x, -1. Over to edit and down to B. Make sure you go down to B after you move over to edit and plug in those 3 numbers. And then after you get the numbers entered in, you need to go back to your regular calculator screen. And in order to multiply the equation, we need to take the inverse of A and multiply it by B. Because right now I have a matrix times the variables is equal to another matrix. We cannot divide matrices. But division and multiplications are inverses of each other. So instead of dividing, if we use the inverse matrix, which is like the pseudo way of dividing for matrices, then the calculator will do the calculations for us. So we have second x, -1, but I just want A. You don't have to do any inserting. Take it to the inverse, and then second x negative 1 down to b. It's a lot of buttons that you're pressing on the calculator. If you put in all the correct numbers, you should get a negative, a 1, a negative 1, and a 2. Which are the same answers of the problem that we did twice. Now we did it 3 times. So we did it the first time with knowing what Z was, the second time using the Gaussian elimination, the third time now with the calculator. So you have 5 questions for homework. No, you can't use matrices only to check your work. You should use Gaussian elimination. The last 2 problems are the ones that you're going to have infinitely many solutions. They're going to be a little trickier because you're going to have to try and figure out how to write that answer using that like order triple tab question.